so far what we have is really just going to take us full circle. We take Hamilton's equations, we go back, we're going to get the Euler-Lagrange equations back. So we're not really seeing the utility of it yet, but we will. But for the moment, I want to give a really important example. I'll just call it Hamilton and Lagrange. I should write Lagrange and Hamilton. But you know, we have this. I'll put the schema here. You've got your L of the Q dot, and P. Then you get this energy here. Sum over. And in many cases it equals T plus U, but not always. Minus L. And then you've got this PI equals dl dqi dot. And if you could turn this into an expression that only depends on the Q's and P's, so you can eliminate all Q dots. There's your Hamiltonian, and it's the energy. So that's why I've got these three steps here. So the simplest example, once again, so if we have L as a half m x dot squared minus u of x, then the energy is going to turn into a half m x dot squared plus u of x, and we're going to have P equals m x dot, and so the Hamiltonian is going to be E squared over 2m plus u. And with different coordinate systems, we just get a different version of that notation. So that's the quick version here. And of course, the Hamilton equations of motion are now, I'll put it in general. So for the multivariable version, you've got qi dot partial h, pi dot minus partial h, partial qi. And if you do that, you come full circle and you just have the Euler-Lagrange equations, which are the Newton's equations all over again. Okay. We're going to take it another step now for a really important example. And the example, which is going to be a homework problem, and I'll just get us started on it, is this. The Lagrangian for a non-relativistic charged particle in an electromagnetic field. So, non-relativistic Lagrangian for a charged particle. I'll just write for a charged particle. It looks like this. 1/2 mv squared minus q times phi plus q a dot v. And we're going to explain this a little more. Where minus gradient of phi equal to E, and the curl of the vector potential A is equal to the magnetic field. So is that familiar territory? Have you guys had the vector potential before?
Yeah.
Good. 107A, already have that. So we have to prove this. What do we actually have to prove? We want to show that the Euler-Lagrange equations, so homework, show that Euler-Lagrange equations lead to M, down here at the bottom of the board, equals QE plus QB cross B. You guys recognize this too, right? Force on a charged particle, electromagnetic field, you've got the charge times the electric field, and you've got the Lorentz force D cross B. So this is a good one, and after that, we're going to construct the Hamiltonian as well. So I'll show us how both of these go, and yeah, this one plays a big role. Especially when you take quantum, and you're going to wonder, yeah, where does this Hamiltonian come from? But we're going to derive it now, or get a start on it. So what we're going to do is begin with the Lagrangian. So what we've got here is a half, and we'll work in Cartesian coordinates. So x1 dot squared, x2 dot squared, x3 dot squared, minus q phi of x1, x2, x3. Now this last thing here, I'm going to write q a of x1, x2, x3 dotted into vector x dot. Okay. So we got to have all the components of everything up here. So this is a dot product. So this would be q a1. I'll go ahead and just write a vector x x1 dot plus q a2 q3 dot.
Q wants to be a vector.
No, q is the charge. Q is the electric charge. X. Q.
Can't confuse with the generalized coordinates.
Yeah, that's right. Then brought that up. Q is the electric charge. Phi is the electric potential. And A is the vector potential. So this is a really good one to work out your Euler-Lagrange equations. And in fact, if you can get the first component, you'll be in good shape. Because the second and third are just cyclic with the first component. You know, if you just named them I, J, and K. So yeah, that's the Lagrangian. What are the Euler-Lagrange equations? We'll say for x1. And you'll see, it'll suffice to do it for x1. So we would have d over dt del dx1 dot minus d del dx1 equals 0. This time there's a bit going on. In fact, let's just kind of put this together here. dl dx1 dot. What do we get here? This is, remember, this is actually the generalized momentum. by the way, like I said, this is actually equal to d sub one, because we're gonna construct the Hamiltonian of this problem as well. So here's where it gets interesting. d over dt of dl dx1 dot. What do you guys think we have now?
Definitely that's x1 to the dot.
Definitely this.
X0.
Nope. Because it's a complete time derivative, we've got a bunch of chain rules. This is a1 of x1, x2, and x3. So remember, we have partials, and then we just, have the explicit expression, but the complete time derivative has the chain rule in there. In Raunchy mechanics, chain rule all the time. So remembering that, now what do we get? Yeah. So, but 1, 2, and 3. See, this x is actually 1, 2, and 3 as a vector x. So we've got that chain rule. Should I write it down here? Let me go ahead and erase this. A little more room. So we would have q dA1 dx1 dx1 dt plus q a1 x2 plus q a1 dx3. So this is actually all p sub 1. But remember, it's got a lot of work to do because we want to get this out here. So, and I'm not going to write it out, but your dl dx1, you go back up here, and what are you going to have? You're going to have minus q phi d, q d phi dx1. Let's put an extra line sign. But then when you do the derivative here with respect to x1, each of these has an x1 in it. Right? So I'll just do that one in red. This one's got a bit of bookkeeping, but it's good for you. Okay, so you've got q a1 x1 x2 x3 x1 dot plus the other two. So dl dx1 is minus q d phi dx1. Okay. And then I'll just get the ball rolling here. Plus q d a1 dx1 x1 dot plus a couple more of those. So you have to do all the bookkeeping, and the way to do this, then you have a whole big string of stuff, and then you can work your way backwards because you know the definitions of E and B. Okay. So yeah, you gotta have done this one at least once in your life. So for example, we're just going to compare to this guy here, and we would have mx1 double dot equals minus q d phi dx1 plus q, and I'm just going to write sure that the result of this matches up with the result of that, and then you've got the proof. It suffices to do it for x1 because these things are cyclic. Okay? Works for x1, works for 2 and 3. In fact, this is going to be a mix of the 2 and 3 components. So that's the first part of the homework. And like I said, the grand result, the Euler-Lagrange equations give you this. Very important. Those are the vetted equations of electromagnetism after all. So that's important. And once you have that, we can ask about the Hamiltonian for this Lagrangian, and that's also the homework. That'll make a good assignment this week with the other stuff and this one as well. Good. So I'm going to leave the left half up. Can I erase the right half here? You guys have this? So yeah, that's your homework, and this is the grand goal. Okay, so you'll know it when you have it. Okay, you'll know when you have it. You get cancellations, and just expand this thing out using the determinant rule, for instance. So then you'll know exactly what terms you're looking for and comparing right there. Okay, good. So I'm going to erase this. So next we need the Hamiltonian. And for that, I'm going to erase this. So this is also homework. Construct the Hamiltonian. And there, you know, we have to do what we always do. Expand this thing out completely, and then express all of your x dots in terms of this. So here, P sub 1 is equal to, right here, and x1 dot plus q a1 on the vector x. So what's x1 dot equal to? Yeah, and that's going to be key. That's going to be key. So in here you have to replace all the x. I'm sorry?
You want this over M2.
Yeah, x, of course. Yeah, so you've got this thing here, and you just follow these rules that we had before, where you form the DL, you form the energy expression, and that'll actually get rid of this guy in the energy, and it'll come back, because then in your Q, in your x dots, you're going to make this substitution. And I'm just going to give you a hint here. When you square these, don't multiply them out. Just say for x1 dot squared, which is what you need, you just keep it in this form. P1 over m minus q over m a1. Yeah, I'll just write a1 in this form. Who knows about x? So write it in this form, and in fact, you could say 1 over m squared. P1 over qa1 squared. If you leave it in that form, you'll see why. You'll definitely see that's the way to go. And so you're going to get a really famous Hamiltonian, and you can look it up and see that you got it right. But this is the Hamiltonian that you're always going to use in atomic physics. So now you're going to know where it came from. So that way we'll be ahead of the game. So when you see the Hamiltonian in atomic physics, it's always got the vector potential in there, and you're asking yourself why. You know, this P minus Q business is what you'll see. So yeah, when you get the Hamiltonian and the Euler-Lagrange equations, then our work with this is done. Okay? Because what did we do last semester? We solved some of these dynamical problems. That doesn't change. Okay? fact that this Lagrangian gave you that Lorentz force and all means that's the thing we saw last semester. But, and the same would hold true for Hamilton's equations. They would give you back Newton's equations, but the Hamiltonian is what you're going to carry on into quantum mechanics. So good. Okay, good. That's so what do we have now? We have the stuff from the exam. We have the Hamiltonian of the spherical polars, and we have this problem. So that's a good set. So Friday, you guys should knock some of these out. Any of them, really, any of these things. Partially or the whole thing. And I will erase this now. So there's one more thing. There's one thing now that we're going to talk about that Hamiltonian mechanics does that Lagrangian mechanics cannot do. And that is have a phase space. Have you guys heard about phase space yet? Maybe in thermo? In what
You can
class?
describe a particle by, position, velocity, momentum, all of that. Just put all of that in one space.
Yeah, where did they teach that?
Maxwell Boltzmann distribution.
Okay, good.
Have like velocities.
Very good, yeah. So in statistical mechanics, you get phase space. So let's have a look at what's going on with phase space. Because so far, we just turn the crank and we get the equations of motion back that we already would have had. But phase space is something new, so phase space. And that is the set of all points QE. So the idea is we're going to have a Hamiltonian system, Q1 to Qn, P1, Pn, and we're going to have energy is conserved, so no explicit time. It's conserved. And we have these equations of motion. Ui dot equals EH EI dot EH QI. So that's our, one of them gets a minus sign, there we go. Yeah. Dot, that's Newton's law, it's a minus sign. So there's another way to interpret these equations, namely as the complete time derivative of a 2n dimensional vector, a 2n component vector. And the right side, so that's a 2n, right, 2n components. And the right side of this would also be a vector. I'll write it this way, dh dpi, and the vector there minus partial h dpi. The vector there. So that's a way of writing that. But this is the first derivative of a vector. What's the first derivative of, say, a position vector? Velocity vector. So we can think of this as a velocity vector in phase space, and that means the velocity vector of a point in phase space is given by a vector field. So 2n components, this here is a vector field. Now, there are, say, 1,000 gas particles. And how many components does this vector fixed and. Oh, 6,000, right, you'd have 6,000 components for 1,000 gas parts. Because each one has its X, Y, and Z, and P, X, P, Y, and P, Z. So yeah, that's a lot of components. Good thing we don't have to calculate them any time there's more than two. But what that means is the motion of a physical system is a point in this gigantic phase space. It's the motion of a point, and that point, is moving like a velocity vector here. So yeah, let's look at that. We'll do this, of course. The one we can visualize is for n equals 1, because we can draw it on the board. Everything else we have to use our imagination. So the phase space, if we're just using our imagination, we'd say it's got n components here, and n components here. So you can't really visualize it. But for n equals 1, we really do have this Q and P. And any point in phase space here, it's moving. And since it's a, complete time derivative of this vector, so if it starts here and ends up there, then this guy here is your d over dt qt. For example, say something we're going in a circle. Okay, you know what? We're going to see in a minute, it's always clockwise phase space. So say something we're going in a circle, then the vector field associated with this motion will look like this. I can't draw that many arrows. You guys can get your machine to construct a nice vector field. Little arrows everywhere. So let's put this in words before we calculate anything. So what we're looking at is a motion of a point in phase space. It's true for any of these dimensions, but for n equals 2, we can actually see what's going on. So we got to be concrete here. Let's consider the harmonic oscillator. This one we can get a lot of mileage out of. So the harmonic oscillator, let's say we know it's Hamiltonian. E squared over 2m plus 1/2 k squared. Not k squared, 1/2 kq squared. Everybody agree with that one? Hamiltonian harmonic oscillator. And we use kx squared, so kq squared. Energy is conserved, so we can write E equals E squared over 2m plus k squared over 2. And if we want to get some information about what's going on in phase space, we can write it this way. P squared over 2me plus q squared over 2e over k equals 1. And what I can do, square root of this squared and the square root of this squared. And what have I constructed here? Equation of, back up to here. Here would be, what do we have? You guys recognize that? Oops. value of E, we have a nesting ellipse. So for a certain E, we have this ellipse. For a smaller E, we have that one. For a bigger one, we have that one. So this gives you an ellipse. And what we'll do next is we'll show that Hamilton's equations for any given E will give us a vector at each point that is just tangent to this ellipse. So there's a whole vector field here. And they would be longer the farther out you go and shorter the closer you go.
Use the same constructions that planetary motions.
Not the same, not the same construction here. But we did use this form when we needed the area of the ellipse and stuff like that. When we were doing Kepler's laws, we were getting used to this. Then we had 2A and 2B and so forth. So, okay, we're erasing it over here. What are we doing? Yeah, we got this. So, we're doing phase space, n equals 1. And what we want to look at now is this differential equation. Okay, so I'm going to go ahead and just rewrite this. So yeah, these are these curves of constant energy. But let's go ahead and look at harmonic oscillator again. So we've got h p squared over 2m plus k q squared over 2. We have d over dt qp. So q dot is dh dt. We go ahead and write this out. So dh dt minus dh q. So what do we have here? dh dt p over m minus dh dq minus kq. P dot minus kq. And of course, P dot is going to be, we get M Q double dot equals KQ, right? That's going to be Newton's law for this. But right now, we're just looking at this as a vector field. And I'd say the easiest way to look at this as a vector field for starters is just let M and K be equal to 1. Okay. Let M and K be equal to 1. And say we want the vector right here. So right here, P is equal to P naught, Q is equal to 0. So this vector would be 0, P naught, right? And the vector field, actually, that elsewhere here. So this vector here is 0, all this P naught. And what's the field vector?
Should it be like P9 and 0?
No, because this is the Q component. I put the Q on top,
Oh, okay, got it.
like X, Y.
Yeah.
So 0 P naught. But what's the vector field? The field vector is this one. So P naught negative Q. Okay. So the field vector, just going to write it here. P naught over M negative K Q naught. That's P naught over M 0. That means the field vector is pointing there. It's got x, x, y.
So vector QP basically determines the state of the particle, and when we take the derivative, we get like dH to D, dH to Q. It's
Yeah.
a vector field that tells the particle where to go.
Exactly. So this side is the thing that you can say is driving the point, and this is its motion. So the right side is all just geometry. You can construct all these arrows, and what you're going to find is that they go clockwise. this one here is going to have a bit of each, so forth. So yeah, what you have here is a circulation. If you were to draw a bunch of vectors, maybe you guys should program Mathematic or something. And draw, can you guys do that? Have it print out something like this, with little arrows. They'll be longer up here and shorter towards the middle, and they will, for the harmonic oscillator, they'll circulate around they'll circulate around the origin. And it looks so much like a fluid flow that it's called the phase flow. The motion of these points is called phase flow. So, put this in words now. We have the motion of the point phase with the harmonic oscillator. And we can see now we're going to get little arrows here with a bunch of important points to mention now. These curves do not intersect. Right? These curves don't intersect, they're completely nested. And what would it mean for two phase curves to intersect? Because each point is an initial condition. Each point represents an initial condition, and if we had intersection of two curves, we would have an initial condition that has two possible outcomes.
Energy would be conserved.
It's not so much energy would be conserved, but uniqueness of the solutions wouldn't be maintained.
But if each curve is at a different energy level, as you said, very E, we have like different shells, so to speak.
Yeah,
They intersect.
Yeah, if they intersected,
You can jump from one shell to another essentially.
well, in this picture, they can't. Right? They can't intersect at all. I'm just saying, if you had a phase curve that intersect, you would be violating the uniqueness of the solutions. So they don't intersect in general. It's an important point. The phase curves do not intersect. Do not intersect. So, yeah, I can draw a gazillion arrows, but that's how they're constructed. So the point is that the right side here, this is the vector field on the phase space. So Lagrange mechanics doesn't have this. You get this at the cost of doubling your number of variables. But that is what took you down to a first order instead of second order equations. And so now you have the motion of the point. Motion of the point in phase space. And if you take an initial condition and just follow it around, that's called the phase flow. So I want to add that to the notes here. Each point in phase space has an initial condition. Initial condition. And now we'll just follow one around here. Perfect. Phase space initial condition.
I have a question.
Yeah.
So let's say, the system was like losing energy over time.
Yes.
I think that, a vector would gradually, it would still go around the circle, would it like spiral inwards?
Yeah, that's a perfect point. I was about to bring that one up. So we had these concentric ellipses, but if we had damping in the system, if the energy were not conserved, then yeah, it would spiral in towards the center. So yeah, the shape of these is really crucial as well. We're going to generalize this one next time. We're going to generalize it to the pendulum that can do full 360s. Okay? The rigid pendulum that can called the rotator. And but for for the moment, we have to stick with this one here. Let me erase a bit just so I can get a new picture up here. So we have everything we need. We've got this, we've got that. So let's follow an initial condition around it. This is our harmonic oscillator. We know this thing well. So suppose this is our initial condition. Okay. What's the next thing it does? Its vector, its time rate of change given by that vector field is p over m minus k cubed. Okay. This time it has a 0p minus k times the cube, so that's why it's in that direction. Okay. And what are we talking about? It's a harmonic oscillator. If I were to have Q in this and start here, just imagine that I'm oscillating back and forth. Right? Harmonic oscillating back and forth. Then I'm going to have my highest speed when I pass through the origin. When I pass through the origin, my Q will be 0. Negative velocity maximum. When I get here, I'm going to have 0. I'm going to be at minus Q, but I'm going to have like that. Because that's that component of the vector field. Okay. So yeah, we're going around in this circle here, or ellipse, as we want. So yeah, you can see it's always clockwise. And what we'll do next time, I'll just set this up for us, that way you guys can remind me. So next time we'll set up the pendulum. But it will be fully 360-degree compatible. We'll have phi here, and the thing will be capable, and L, the thing will be capable of doing a full 360. And we'll get its phase space and its phase curves, and they will look like this, but then they'll do something different when you get to the point where it can rotate. In other words, the little harmonic oscillator version is going to look like this. But the full rotator version is going to look a little different. So anyway, that's where we're headed now.